Hello, everyone. We're in science now, and here's messed up. We're in science now, and we're going to be studying a lot of physics, Newton's first law. Caleb and Cash, your older sisters, will know this stuff well. They can help you. They'll be happy to help you if you need any help with any of this because they took this stuff early in the year. This whole chapter is going to be on Newton's laws, and this first chapter is going to specifically be about Newton's first law. Okay, so turn to we're in unit F now. F for physics. No, just kidding. Physics starts with PH. But page F6. Okay, the first thing you see those two little girls playing with the car and the truck and the. Oh, I thought it was a skateboard at first. That little thing that she has is a weight. Um, they were checking the masses of the different vehicles. So what we're going to talk about is some different vocab words. So I posted on the science section a little study guide. It's called Science Chapter 14.1 Study Guide, I believe it's called. And what you should do is you should either print that out or have it open while you're watching this video, and you should type in or write in the different definitions of the different words, because we're going to be going over different words and talking about their definitions, and I'm going to give you a quiz in the next couple of days about these definitions. So it is your responsibility to write down the definition. The first word they're going to come to is force. A force is essentially, it's one of those words that everybody knows what a force is. Like if I said, I'm going to exert a force on your face. And so you'd be like, oh, I know what a force is. I'm sure you'd understand what that would be. And so, but it's one of those words that's hard to define. A force is essentially any push or any pull. Anytime you exert a force on something, it's either a push or a pull. If you punch something, that would be a push. If you drag something, that would be a pull. That's what a force is. You're exerting a push or a pull on something. One thing we see about forces that we're going to talk about in the next lesson is that objects with more masses need more force exerted on them. They move more slowly when the same force is exerted, in other words. And so we talk about, I'm going to talk about next time, but directly and indirectly proportional. Force and mass are opposites, meaning when something happens to one of them, the opposite happens to the other one. When you add more force, you have to add more force in order to get the mass to have the same speed. If I want to move, if I want to throw a golf ball, I have to, and I want to throw at a certain speed, I don't have to add as much force as if I would with a bowling ball, obviously, right? With a bowling ball, in order to give the same speed, I have to add more force. So mass works the opposite of force. It kind of slows force down. It adds more. You have to add more force to it. The next word we come to, I think they kind of do these out of order. I know you guys have on your little study guide they're just in alphabetical order, but I wouldn't have done inertia yet, but we'll do inertia. Inertia. This is what Newton's first law is all about. I'm going to talk about Newton's first law in a minute. But inertia is a tendency. It's not a speed. It's not a force. It's not a whatever. It's a tendency. It's something. It's a characteristic that all objects have. What inertia is, it's a tendency to resist change. Whatever that object is doing right now, it wants to continue doing that. If your couch is sitting still on your living room floor, it wants to just continue sitting there, okay? And you go to push it, and it resists you pushing it. If your couch was on wheels and rolling very, very fast down a hill, it wants to keep doing that. And you standing in its way is just going to hit you and knock you right over, right? And so whatever it's doing, it wants to continue doing. And you can think of that, and it's not one of those things where if you're tired and you're in bed, inertia is causing you to be like, I don't want to get out of bed. That's not really the same thing. That's just you being lazy, or me being lazy. But inertia is, with motion specifically, a tendency to resist change. Next page, F8, we're going to talk about friction. Friction is a type of force. There are many, many types of forces. We talk about forces as a push or a pull. There are many forces exerted. There are forces exerted by like a string or a rope. That's called tension. You know, if you have a rope and you pull it as tight as you can, that's called tension. Or you're sitting on a swing, those swing ropes, that's tension. Your weight is a type of force, which we're going to talk about. Actually, I think we already talked about that in the previous chapter. Weight is a type of force. But friction is also another type of force. Friction is a force that works to impede or stop motion. It works against the direction. If you are traveling this way, friction pushes back this way. If you're traveling this way, friction pushes back that way. Whatever it is, friction just wants to bug you, and friction wants to move and do the opposite thing that you want to do. But we have to live every day. Friction is very, very important in order to live our everyday lives. One of your assignments today, it's just a mental exercise. I want you to think about what life would be like without friction. Think about it. What would happen if you go and reach for the doorknob? You go to turn the doorknob, your hand just slips right around it because friction is what gives you grip, right? It impedes motion. So you go to turn that doorknob and your hand would slide right around. You wouldn't be able to grip it. I can hold this book right now because of friction. The friction between my fingers and the book causes me to not drop the book. Walking across the ground is by friction. Your friction of your feet, your shoes on the ground cause your feet not to slip. Without friction, it would just never be able to get traction, and you'd be sliding all over the place. So friction acts against moving objects. Now, we come on F8, the last paragraph. It says 45 years after Galileo died, Sir Isaac Newton published a complete description of the concept of inertia. It's called the Newton's first law of motion. Newton's first law of motion is all about inertia. We were just talking about friction, inertia, whatever. It's all about inertia. And this is what exact wording of what Newton's first law is, okay? An object at rest is going to stay at rest. And an object in motion is going to stay in motion in a straight line at a constant speed as long as there are no other forces acting on it, as long as the amount of force on it doesn't change. And you can experience this, Newton's first law, which is inertia, when you are driving in a car. Okay, you're driving a car, minding your own business, looking around. All of a sudden, Mom slams on the brakes because a squirrel comes out in the middle of the road. Or maybe your mom slams on the gas because a squirrel comes out in the middle of the road. I don't know your mom. Maybe she's like that. I'm just kidding. So let's assume she slams on the brakes because she's kind to animals. She slams on the brakes because a squirrel darts out in the middle of the road. What happens to you? You go like this, assuming you're wearing a seatbelt, which you should be. You go right into the seatbelt, right? And you feel like it presses against you. What's happening there is that your body, because of inertia, wants to keep moving forward. It wants to keep going along the road. But all of a sudden the car is stopping and your body wants to just keep moving forward. But the seatbelt keeps you in place. So that's why you slam against the seatbelt. And that's what's really important to wear a seatbelt. Think about what would happen if you were going fast and you weren't wearing a seatbelt. Your body would just keep going right into the windshield, which could kill you. And so that's why it's important to wear a seatbelt. Think about what happens when she takes a turn. If she takes a turn going, fairly decent speed, you feel like, whoa, or she swerves around somebody's barrel, rolls out in the middle of the road when it's windy. She has to swerve. You feel like you're slammed against the side and then slammed against this side because your body is like, we go this way. I want to keep going in a straight line, right? I want to keep going at a constant speed, the same speed I was going, right? Or if you're sitting in the car and you're in a souped up car and they slam on the gas and you feel like you're pressed back into the seat. Maybe you're at a ride at Six Flags or something and you feel pressed back in your seat because it all of a sudden accelerates really quickly. That's because of inertia. Your body now it's sitting at rest. It wants to stay there. Now it's being pulled, and then you feel like your body. That's Newton's first law of motion. Your body wants to keep doing what it's doing, staying at rest or moving the straight line at a constant speed, and it will keep doing that unless some force acts on it. That's why if you were in an environment, now in our environment right now, there's always friction. Friction can be caused by anything. The opposal of motion. The ground causes friction. Even the air can cause friction. That's what you're feeling with wind particles. But out in space, there's no air particles. So there's no friction anywhere other than if you just were slamming into a rock or slamming into a planet or slamming even into dust or debris out in the universe. But if you are in the universe and there was a huge, let's say, huge space shuttle just sitting there, okay? If you were to go boop, and touch it and just flick it, okay, what would happen is, because even though that's a small force, that thing would be propelled forward. It's nothing, no friction's holding it back, and you would flick it, it would all of a sudden move very, very slowly. It would move, and then it would keep moving literally forever. If you took and you had some sort of anchor to anchor yourself, and you took your hand and pushed that space shuttle, you could sit there and throw that space shuttle across the entire universe, because it would not, and it wouldn't be stopped. You know, you'd have the world record for longest, or you had a baseball in your hand. You throw the baseball, it literally would keep going across the entire universe. You have the world record for longest baseball throw, and it would keep going because nothing, no friction would stop it. What literally would most likely stop it would get pulled in its gravitational pull by some planet or object or something. But you know, F9. How inertia works, I kind of already explained that. F10. Where is it? All right, so where things are can be found. That's called your position. Where you are at a particular time is called your position. For instance, my position is in this room in front of this computer. I could say wall is right here, 2.5 feet from this wall, 3 feet in front of a window. I'd say about 12 feet away from that wall, about 12 feet away from that wall. That's my position, right? I could say in the bedroom that we are currently living in before our house, before we get into our house, stuff like that. So that is your position. You can see in this coordinate plane. Remember, we've dealt with coordinate planes in math. Here, there's a coordinate plane. Instead of being an x-axis and a y-axis, each with numbers, here the x-axis has numbers and the y-axis has letters on page F10. And so it's kind of fun to be able to do one like this, where it tells you the different locations. For instance, look at Nashville. Nashville. Now this time it's a little bit confusing as well, because now it's talking about the spaces between the lines. In math, we talk about where the lines are. This one's the spaces between the lines. So if you were to find Nashville, which is in Tennessee, there, Nashville is in D11. D over to from the left and 11 down. And where would let me ask you, where would find Memphis, which is right near Nashville, find Memphis, and who knows the correct answer? Where would it be? Let me call on Kayleen. What do you think? Correct. That would be F4. Oh, F4? Yeah, F4. That would be F4. Correct. Or Atlanta. Atlanta would be J16. So you'd be able to use this coordinate plane to find position. Look at the F11. Now you can see by on this coordinate plane, they show you the position of an airplane at 4 different time intervals. Okay, 4 consecutive times. It's not 4 different planes flying in a row. It's the plane at position 1, plane at position 2, plane at position 3, plane at position 4. And so we see it travels like this, up in this direction. Okay, it's going over the lake as it's progressing. It's starting from Broadway Street and it's going over Paradise Pond. At position 3, it's finally starting to reach Paradise Pond, and by, I would say, it looks like position shortly after position 5, if we were to put a position 5 in there, shortly after that, it would be done with being over the lake. Well, can anybody tell anything about its speed from this picture? Well, first of all, what is speed? Speed is a measure of how fast something is going. Speed, interestingly, let me get my handy-dandy little whiteboard here. Speed, interestingly, is given by this equation. First of all, speed is represented by the letter v. Okay. The reason why it's v is v stands for velocity. Velocity and speed are essentially the same thing. But velocity tells position, tells direction. Like, for instance, if I were saying I'm driving 50 miles per hour, that is speed. If I'm saying I'm driving 50 miles per hour north, that's velocity. So they're essentially the same thing, but velocity has direction. But either way, the speed is given by v. Okay, v equals, and this is the equation, d over t. That's my fancy t. The reason why I make a t like that when I'm doing equations is so you don't confuse it with a plus sign. So V equals d over t. This is the equation. What this is talking about is the speed is equal to, how you find the speed is you take the distance and you put it over, or you divide it by the time. Okay? For instance, and you actually already know this, right? If I were to say I'm traveling on the highway, I'm driving 65, what? 65 bananas, 65, what? Well, you'd say miles per hour. Well, when you have miles per hour, it's a distance over a time. Miles, and the word per just means divided by, miles per hour. Miles divided by hours. So you figure out what distance you went, let's say 10 miles, and let's say we're running because this is slow, in 2 hours, okay? What is that? That would 10 divided by 2 equals 5 miles per hour. 5 miles per hour. And that's how you get this equation. That's how you figure out speed. You take your distance that you traveled and divide it by the time it took to travel that distance. And you can do that with any, and you don't have to use miles per hour. You can use any unit of distance and any unit of time. What's another unit of distance? Another unit of distance would be like feet, right? What's another unit of time? Seconds. You could have feet per second. How many feet do you go every second, right? That was how many miles do you go each hour on average. How many feet do you go each second? You could have how many yards per minute, how many yards you go every minute. You could have how many millimeters you go every year. Millimeters per year would be another unit of speed or velocity, right? You could do whatever you want. Light years. Light years is actually, this is a confusing one. Light years is actually a distance. It's the distance that light would travel in a year. So 1 light year is a distance. So you could do light years per second if you wanted. It would be a little confusing one, but any distance. You could do centimeters per month. Okay, a distance over a time. And that's speed. Okay, speed takes your distance, which is and all distances is how far it is between 2 points, right? If I have, this is position 1, this is position 2, that's about 8 inches right there. So that is my distance, 8 inches, position 1, position 2. And I take that distance, 8 inches, divided by how long it takes to get from one place to place, let's say in seconds, and inches per second. Got it? You're going to have to do some equations like that. Let me actually ask you one. Okay, you should be able to do this in your head. What if I'm jogging and I run 20, or I'm walking and I walk 20 feet in 4 seconds? What is my speed? Yes, very good. 5 feet per second, right? Take the distance and divide it by the time, and you get your speed. Next, velocity. As I was explaining on page F12, velocity is the same thing as speed. It's how fast you're going, but in a direction. Okay. Now you have, and your direction can be indicated by a lot of things. Usually it's north, south, east, and west, but you could say left or right, up or down, even positive and negative. You could have a positive direction and a negative. If I said this is the positive direction, this is the negative direction, positive and negative, right? And that's velocity. Next, acceleration. And we're almost done. Acceleration. What acceleration is how the speed or velocity has changed over every second, right? How the speed or velocity has changed each second. So your units for acceleration are going to be your unit for velocity. It's going to be a little tricky. Unit for velocity or speed, and then divided by another time. Because what's happening is whenever you hear per second, per hour, a per time like that, it's called a rate. Like I could have, how many donuts can you eat per minute? That'll be donuts per minute. That'll be a rate, right? Donuts per minute. Punches per second, right? Those are all rates. So speed is a rate, but it's a distance per time. So it's your rate of how much distance you cover. Well, acceleration is how much speed per time. So it's meters, it'll be like feet per second each second. So feet per second, which would end up being feet per second squared. It's a little bit confusing. But essentially, your acceleration is how your speed changes. There are 5 types of acceleration. There is, oh, a very nice, a cardinal just landed outside my window. How beautiful. And it's gone. He doesn't like physics, I guess. So there are 5 types of accelerations. There's start moving, stop moving, speed up, slow down, and change direction. All of these are accelerations that we can do. You have start moving and stop moving. You're changing what you're doing. Your speed is changing because you're going from 0 to something or something to 0. Speeding up and slowing down, you're going from like 20 to 30 or 30 to 20, something like that. And then the special one here, change direction. You might be like, change direction? How is that an acceleration? Because an acceleration is how your velocity changes. Remember what I said before? The velocity is how fast you're going in a particular direction, right? And so if I'm saying my velocity is 20 miles per hour south, and now I'm going 20 miles per hour west, didn't my velocity change? Yes, because I was going, how big my velocity was, my magnitude did not change because 20 and 20, but my velocity changed. One was 20 miles per hour south, one was 20 miles per hour west, okay? And so that would be an acceleration. That would be a change. Any change in velocity or speed is an acceleration. And there's a special word here called deceleration. This is very important. Don't think of deceleration as the opposite of acceleration. Sometimes it can be. But deceleration is actually a specific type of acceleration, meaning to slow down. But an acceleration can be a speed up or a slow down, right? Deceleration is acceleration. But we don't have a special word for going faster. Deceleration just means going slower, right? It means slowing down. We don't have a special word for speeding up, so we just call speeding up acceleration, and we sometimes call slowing down deceleration. That does not mean that acceleration is not slowing down. Acceleration is still slowing down. Just deceleration is a special type of word for that. Hope that didn't confuse you. And F14 just talks about things moving in circles. What keeps things moving in circles is that inertia, we talked about this when we talked about our science lesson with orbiting in the planets. Inertia keeps things wanting to move in a straight line, but gravity pulls it back. Kind of like that picture you see with the girl with the airplanes. The airplanes would fly out in a straight line if the strings weren't attached to them. Some people think that's called centrifugal force, which they would say it's a force like that pulls you to the outside of a circle. Like if you're spinning on a merry-go-round and you let go and you start spinning as you fly off and start spinning, they would say there's a force that goes to the outside of a circle. No, it's just inertia. Inertia wants you to go in a straight line. It's not the outside of a circle, it's a straight line. Okay, so that's why centrifugal force actually doesn't exist. It's just acceleration. All right, see ya.